So we stopped after the first question of this exercise last week. So shall we continue with question 2? Or do we want a little like recap of what we were actually talking about?
I'm fine with whatever. Let's see.
Yeah, okay, then yeah, if no one wants a recap, we'll just continue. We're basically applying map functions. So the second question is, how can you create a single vector that for each column in a data frame indicates whether or not it's a factor? Like we've discussed before, when you apply map functions to a data frame, you iterate through each of the columns. So that's the sort of, I guess, axis in which you iterate. So this is as simple as just using this function. So checking whether or not something is factor while iterating through. So I picked this data frame, which yeah, which we'd used earlier in the notebook. And yeah, just let's see if this will run. Yeah, I need to just a sec to run the library. Oh, I can just go. I'll just run all the chunks. Yeah, so basically, in order to check whether or not each column is a factor, you map is factor function to the data frame that you're interested in. So in the original empty cast, there's no factor, but in one of the previous exercises, we turned the manual versus automatic column into factor, if you remember. Just let me run that, just so you see it. So this is the data frame that we have. This is a double, 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 double. This is a factor. And double again. So we basically expect to get all falses except for the third last column. All false except for the third last, which we turned into a factor in a previous exercise. Third question: what happens when you use the map functions on vectors?
So
yeah.
Havva, so what returns is a vector, right?
Sorry?
What it returns, number 2 is a vector, right?
It's a list.
Oh, it's a list. Okay.
But since this is all logical, we could do this, and now with a vector of logical values. If you use the bare map function without any of the suffixes, like double, float, whatever, like integer, character, etc., then you get a list. So if you want a vector, you need to indicate what kind of vector you want.
All right, yeah.
And I think if I do int, we should get zeros and ones. Yeah, so you get 0 where there was false, and 1 where it was true.
Yeah, yeah, cool, yeah.
Oh yeah, so since it says vector, I guess, yeah, we should choose one. Yeah, so what happens when you use map functions on vectors that aren't lists? What does this do and why? So when I run this, I basically get a list with 5 outputs, and each one corresponds to basically running this function, which is getting a random sample from a uniform distribution, and the n is taken as this value. So the first one is pick one random number from the uniform distribution. And then in the second iteration, it's 2. So pick 2 numbers. In the third iteration, 3 numbers, etc. Yeah. So in essence, I think if this is not a list. It looks like it's coerced into a list. So if I run, if I first turn this into a list and then apply the function, like here, I get the same result. If I run just this bit, I mean, obviously these are random numbers, but the output is the same. I get 1. Yeah. So I was a bit confused here. Yeah, because initially I tried to do just list, but this is different. So when you do list, then 1 to 5, you're not turning this into a list. You're creating a list where the first value is this vector, which had initially confused me. So yeah, if you do that, then you get just the 1 value, because your list has just 1 element in it.
That's a bit weird.
Sorry?
That's a bit weird.
It is, isn't it? And also, like, when you run this, you get a random sample, the same shape and like same size as this, which is that value. Initially, I was confused because I thought this would be the same as without having the list, but I think what's happening is it's coerced into a list, so you get the same thing as turning this vector into a list like this. Yeah. Question 4.
Havva?
Yeah.
Sorry, could you run as.list on 1 to 5? I feel like it should be the same result. I don't know why it's bringing something.
I don't think it is. When you run this,
okay.
To a list, so which kind of makes sense. Like that's you go from this, which is a vector, into a list of that, and I guess, like, you know, it would make it a lot easier if I, like, a lot clearer.
Yeah.
If I did that. So you go from the first element, second, third, blah, 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 into turning it into a list.
Okay, so actually now I see the difference. So for example, if you have 3 vectors and you want to turn them into like columns, it will be better for you to do as.list. If you know what I mean. Do you get what I mean?
No, I don't follow, sorry. Say that again.
So for example, if you have the first vector, C 1 to 3, then comma, C maybe 5 to 6. Yeah. Yeah, like that. If you make it as a list, or and then do some kind of function on that.
Let's just see this then.
That's, oh my God.
What? Wait, let's put this into, but I think we're just like, we're going a bit off track now. Just like a sort of confusing ourselves. Yeah, I don't know. But basically, I expected list vector, right? Like calling list function on the vector to return the same thing, but it didn't. It was using the as list function on the vector.
Yeah. Okay.
Makes sense. So you go from basically a vector of 1, 2, 3, 4, 5 to a list where the first value is 1, second value is 2, etc. Yeah. And the 4th question, what does this do? Yeah, so basically we have a vector going from -2 to 2, and we apply the r-norm function on it with n equals 5. So we're basically picking a random sample of size 5 where the mean ranges from -2 to +2 in intervals of 1. So when we have it as map, the result is a list where each element, basically we're mapping a vector of numbers into a list of where each element is like 5 numbers long. But if you try to do the double, you get an error because the input and the output sizes don't match. Because basically for each element in this, you're replacing it with 5 elements, right? So this basically went from -2 to 5 random numbers drawn from a normal distribution of mean -2. So the sizes don't match. The result, 1 must be a single double, not a double vector of length 5 is the error. So in order to accommodate for the size difference, you need to use map so that you get a list output. Does that make sense?
Yeah.
So if I changed it basically to like from 5 to 1, and there's no problem. So there's nothing inherently wrong with this. It's just that when the return value is greater than what was input, then you have a size problem. And question 5, rewrite this to eliminate the anonymous function. So this is basically how to use the shortcut notation for anonymous functions. You just basically replace the function declaration with a tilde. And instead of, like for the iteration input, you put dot. So instead of saying data equals df, you do data equals dot, which means every time you iterate, whatever the current sort of element is in that iteration, use that as the data. Any questions?
No, thank you.
Oops. So the next section is dealing with errors. This is basically for cases where, you know, one of the elements that you're iterating over gives an error, whether it's a type error or, I don't know, something goes wrong with the function that you're applying. And you can use a number of different adverbs to take care of this. You can use safely. Basically, what you'll get is 2 lists. One, which is the result for cases where there wasn't any error. And the second is error, which contains all the cases where there was an error. So if you run that, we basically, in our list, we have 110a. When we apply the log function, we expect to get a problem with a because it is not a number. And we can see that. So basically for the first value of 1, we get a result of 0, which is what we expect when you apply log to 1. And for the error, we don't get anything, we get null. Second value, again, we get log of 10, and for error, we get null. And for the third value, which will have an error, we don't get anything for the result. But for error, we basically get an error message, an error call, and attributes, and all the rest of it. So you can handle basically errors in using this. And you can, rather than having a list of lists where each element is like result and error, you can transpose it so that you have a results list and an errors list, which is a lot easier to handle. There are also other adverbs in per, which again do similar things. Possibly, basically gives like a default value where there was an error, and quietly does a very similar thing to safely, but instead of capturing errors, it captures printed output. So in essence, the function runs quietly rather than printing errors or warnings, but you get that result in your variable or whatever you're using. I think this is a good point to maybe look at like some of the exercises from the exercise, like the website I sent. unless you wanted to just like finish everything here. Shall we have a like apply what we've learned so far with this gapminder data set?
Good. You can do that.
Yeah.
Yeah, you can go. You can.
So basically, I don't know if you've had time to have a look at this, but I found this sort of tutorial quite useful to apply some of these ideas and like, you know, these functions and functionals into some real life problems. And here we're basically using the gapminder data set. So one of the examples was here using map to basically do some initial data exploration. So if you wanted to find out like what's the data type of each of the columns in the data set, like we've seen already with some examples, you can run this, or like how many distinct values each column has. Again, you can apply this time with an integer, which is again quite similar to what we've seen. And if you want to see both of these values together, so we want to see that, for example, country has a data type of factor and has 142 distinct values, and you can imagine there could be lots of other things that you might want to sort of summarize and explore your data with. So I was initially tempted to just like put the functions in a vector like this and then just see what happens. But actually what this does is it applies them in succession. So it applies the first function and then the rest. So in this case, I use the map df function. So this is basically apply a function and as a result give a data frame. And here basically my data is the gapminder data set, data frame, which is here. And I'm applying a function where I'm creating a data frame with the columns data type, distinct values, I don't know, maximum, mode, etc. And this basically gives me this like summary data frame where I have, you know, the first column has data type factor, has 142 distinct values and mode of Afghanistan. So this is the most popular value in my first column. And there's one helpful thing as well, which is this .id. So when I've done this, I've basically lost the names of the columns. Now I don't know which column this refers to. I can sort of go back here and go, okay, so the first column is the country. So this row refers to my country, sort of variable, right? And my next column is continent. Okay, so continent is also a factor of 5 distinct values where the mode is Africa, etc. So if you use this .id variable, .id argument, you basically also get the names of each of the elements. So as map iterates through this data frame, column by column, each column's name is accessible through this .id. So if I run that, I kind of get the same data, but now I also get the variable name that, I mean, I've chosen that name, you could choose to call it whatever you like. So I know that the country column is a factor of 142 distinct values with a mode of Afghanistan, etc. Which I thought was quite useful. So you can, if you want, write your own sort of exploratory functions like this to summarize the data, to get an idea of what sort of data you're dealing with. And there are two sort of variations of map_df. So the default is by rows. So here we're basically we've iterated through this data, and for each iteration, we have added a new row. You can also do it by column. Let's say, I don't know, if you had, let's say if you had like a data which is all text, and you wanted to make everything uppercase, one way you could do it is basically iterate through everything and apply string to upper to each one of them, for example. In this instance, like this column-wise iteration isn't very useful, but I was sort of like playing around with it just to see. It's not, as I said, like doesn't really give any meaningful information, but I just wanted to show it as a, like the difference between them. So instead of like, so factor n 142 is from the first iteration, and then factor n 5 is from the next iteration. And you can see they are sort of glued together column-wise rather than row-wise we have here. Any questions?
No.
So I'll go through the book again. So this was, I think, until where we covered now. So far we've looked at basically how to map over a single list or vector and use that as an input. But we can also map over multiple arguments. Oh yeah, I'll show. Let me just quickly go through the book and then I'll show the examples. So for example, for our normal distribution, so far we've sort of used the means, put the means into a list or a vector, and then we iterated through them, and at each iteration we had a different element of this means list in our functions. But what if we also wanted to change the standard deviation, which is, you know, one of the other arguments that this function takes? Well, we could do that by using Map2 function, which basically does something very similar to what map does, but over two lists. So what it does is, in this case, our sigma is also a list of the same length. And what Map2 does is, for each iteration, basically take the first element from our means list and first element from our sigma list, and then apply the function. So first argument, second argument, function. And again, just like before, we can add any extra arguments into the map function here. So in essence, we're sort of putting them side by side and iterating through them together. And if you're familiar with Python, this is what the zip function does in Python, if you know, that helps. So yeah, we're basically running through them in parallel and then adding any extra arguments to each one. And sort of this could be extended to map 3, map 4, map 5, but it is generalized to pmap, which is basically a parallel map. So in this case, if you wanted to sort of also change the n, it's how big the sample should be, you can also give that as an argument, as like a list to iterate over. And now you basically iterate through all of them side by side. So take the first element of mean, sorry, n, first element of mean, first element of sigma, and apply this function. Yeah. So this can apply to, you know, 3 lists, 4 lists, 5, as many as your function can take. So you can basically have, and you can sort of apply this in a data frame as well. You can have one column for one of the arguments, the next column for the other argument, and then apply your function to each row of the data frame. Like here, for example. Now let's look at some examples. So one of the examples used in this tutorial was, let me just find it quickly. I was plotting basically the life expectancy based on the continents in this Gapminder data set. So we basically want to look at each of the continents in each of the years that we have available in a data frame, and then plot all of the countries in that continent in a plot like this. So we basically want to get this outcome for each of the continents we have in the data set, for each of the years we have in the data set. And each dot here corresponds to a country in this continent in this year, the life expectancy on the y-axis and GDP per capita on the x-axis. So the way we do this is, first, we basically need to get a combination of continent and year so that we can sort of iterate through it. So first, get the continents and the years from the data set, where you just get like all the distinct values of the pairs. And I'm pulling the continent for the continents, I'm pulling the year for the years. And then the next step is basically, we know what we're iterating over. So this is sort of equivalent to, let me find it here, this situation here. So we basically want to have some function which takes our continent and some function which takes our year value and then do something. In this case, we were just drawing a random sample. In this case, we want to plot this graph for each country. So what's suggested in this tutorial is the best way to figure out what needs to go here is to just take one example, take 1 year and continent combination, and figure out what the function needs to be. So that's the next step here. So we'll label x, well, dot x as our continents and just extract the first value from the continents, and dot y from the years. So this is basically what's going to happen in the first iteration of running map. And this is, I don't know, this is the simple graph that I wanted to plot. So basically I take my data set, I filter so that I have only the data from the continent that I'm interested in and the year that I'm interested in. And then I plot basically life expectancy on the y-axis, GDP per capita on the x-axis as points. And then I do a simple title so that I can follow what's happening. So this is life expectancy versus GDP per capita in this continent in this year, and add some labels. Does that make sense?
Yeah, for the continents and years, is it just random that they've chosen to call them .x and .y again? That's not. Yeah. I'm getting confused with the use of the dot notation elsewhere. Right, so that could be anything. Okay.
Yeah, it could be anything, but it's helpful to do it like that so that you know what that maps to. But yeah, this is perfectly fine, and
right,
I'll just do that.
Okay, cool.
That will work.
But you're saying it's helpful because then you'd know which one needs to go on your x and your y axis.
Yeah, I mean, I've chosen x and y because basically that's the notation, right? Or like the
convention.
Yeah, convention. Thank you. So basically, you have like your .f, which is the function. .x and .y are the two things that you're going to iterate over. So I've chosen that so that it's basically, I don't need to do any further translation. Like I could call this, I don't know, continent, and then I could call this year like this, and then figure out my function. And if that helps to think about the function, that's perfectly fine. And then once I've done that, I then have to go, okay, which one is my .x, which one is my .y, decide on that, and then replace them all, if that makes sense.
Yeah, I think I get that, thanks.
So I'll just undo this. And then also, I could have chosen my years to be .x and continents to be .y, all that would change is the order in which I'd put them in my map function. Like there's nothing tying this x to this x. And if you look, I mean, it's not what's on my x-axis. The .x and the .y are just the conventions used for the first list or vector you're iterating through and the second list and vector you're iterating through.
Yeah, I think I've got confused because they introduced like the dot notation at the same time as having this naming convention within per,
Yeah.
and I think I'm just getting them mixed up, but that totally makes sense.
Yeah, I until I saw this example, I was also really struggling. And you know, what we're doing here is figuring out what the .f is. So what function do we want to apply to each element in these two vectors?
Yes.
So once we've figured out what the function needs to be, then we can now map this function to these two vectors. So the third step is, I mean, I'm assigning it to a variable here, but that's not important. So we basically want to use the Map2 function because we are iterating through two things. Our continents list, which again, I could just run, and this is the continents. And our years sort of vector, which are all the years corresponding to those continents in the unique combinations. And the function we're applying, I'm using this shortcut. So it's an anonymous function where for each value, we go into the Gapminder data set, like we did above, filter on the continent and the year, and do a simple plot and label it. And if we look at a random value, I don't know, 2 here, we see we've gone, we're in Asia, 1957. The first value, I think, was 52. Yeah, this is what we built our function on. And this is, let's say, the second value. I don't know. If we look at the 12th, Asia in 2007, etc. So we've basically applied the same function to all of the continent and year combinations found in our data set. I thought it would also be quite helpful to see a comparison of all the continents in that year, because what does this really tell us? Like it tells us the general trend, but like how does, I don't know, Europe compare to America? So I've added an extra sort of function here just to see like how I'd go about doing that. And in order not to make this like a huge sort of anonymous function here, I've defined my custom sort of plotting function. And instead of having this notation, I'm just going to put that function to apply to each element. So I defined my function as taking a continent and a year and some extra sort of variables. So I first prepare like a base plot of all of the continents, and then my data that I want to highlight, which is basically these data points for each one, and then I combine them. So I have my base plot and then add some extra data on top of it based on what data I want to highlight in that iteration. And I've added some conditional things to take logarithms because I thought that looked better. So if I show you the result of this, so if I give my function a continent and a year, it plots, like before, the life expectancy versus GDP per capita in that continent in that year, but it also plots all the other continents in color in the background, and I've also added labels. So in essence, I'm still mapping over two variables, continent and year, but I've added this sort of background. So this was just one example. If I want to then apply this to using map, if I want to apply it to all of the continent and year combinations, I still do the same thing. So my .x is continents, .y is years, just like before. And my function is my custom plotting function, .x, .y. So the first argument is the continent, because that's how I define my function. And the second argument is the year. And I basically get the same thing. So for each different value, I still plot the same thing. If there's too much overlap, it won't label everything, but that's another problem for another day. But now I can see how does Europe in 1992 compare to, I don't know, the Americas in 1992, etc. But yeah, I wanted to sort of explore this just to see like how I would go about expanding like a simple application and using, I don't know, an extra layer. Yeah. So I think that's, oh yeah, we still have some more in the book. Any questions?
Yeah, so I have something amiss when it comes to, for example, PMAP.
Mm-hmm.
Yeah, so if you just look in the book on your right, yeah, when you're creating the list of arguments, should they be in a certain order, in a specific order as the function you're going to apply, or can you just make them in some order as long as you label them somehow?
Yeah, exactly. So if it says here, if you don't name the elements, then PMAP will use positional matching. So if we look at, our norm, if I think the first, I can't remember, but basically, let's go down. 1 sec. So the first argument is n, the second argument is mean, third argument is standard deviation. If you don't label things, then the first value you enter, i.e. in your map, the first thing that you list here will go into, sorry, the first thing is the list, but then, we'll go here, the second thing here, third thing here, or you can label them if you give them names, but then you will use named arguments as opposed to positional matching.
Yeah, I think the named argument like that one there, add 2 is really good.
Yeah, I think it's much better. It's also more future-proof. Like if very uncommon, but like if the order of the arguments changes in the function in a later iteration, this is safer. Yeah. So basically, we're sort of like going further and further away from very descriptively writing what exactly needs to happen. So we went from a for loop where we're explicitly saying what needs to happen in each iteration to a map sort of abstraction where we just gave a list and a function. And then we've gone one level further where we said, well, I have, I don't know, 2, 3, or n different arguments to my function, and I want to iterate through each one of these lists. And the next step of complexity is to say, I'm also going to iterate through the functions that I'm going to apply. So not only, so the list that you're iterating through is or includes the function to apply to. So in this case, the example in the book is basically what distribution to sample the data from. So we're going to iterate through uniform distribution, normal distribution, and Poisson distribution. And we also have a list of parameters that we want to give each of these functions. So for the uniform distribution, we give minimum and maximum. For normal distribution, we're giving standard deviation. Therefore, we're using the default mean of 0. And for Poisson, we're giving lambda. So therefore, using like default. And I think, and for each one of them, we are specifying n. So sample 5 numbers randomly from these 3 distributions with these parameters. So in essence, what we're doing, sort of shown in this diagram. Okay. So the first thing we're iterating through is the function to apply. The second thing is the parameters. And then what we get is we run the function that we chose to use with the parameters in the parameter list and any other argument that was provided in this invoke map functional. Does that make sense?
Yep.
Yeah. And there's also the functional called walk. This is what you use if you're interested in the side effects rather than the sort of output of the function itself. So you, for example, in our earlier example, I was sort of saving all the plots into a list. But if, let's say, the only thing I want to do with them is then save them as a file, then I can add that to my function. And instead of using Map2, I could use walk2, which is basically walk through these two lists using this function and just carry out the function. And as a side effect, I'd put, I don't know, save plot in my function, and I'd basically, I'd be done. I'm not going to use the sort of plots variable that I saved it in. So that's, what we could have done. So walk and all of its sort of walk to pwalk is what you would use if you're only interested in the side effects rather than the output of a function. And there's also some other patterns for for loops. So if you wanted to, let's say, filter your list, you can use keep or discard. So keep is basically go through the iris data set, go through each of the columns of the iris data set and keep anything that returns true for this function. So keep only the columns that are factors. And if you want to do the opposite, go through the iris data set and keep everything that isn't a factor. You could either do keep and then exclamation mark is factor, or you could do discard, which is, go through the data set and discard anything that returns true for this predicate. You can also use sum and every. So if you give sum a predicate, then if anything in the list matches that predicate, is true for that predicate, then you get true. Whereas for everything needs to match it in order to get true. So basically in this list, numbers 1 to 5, letters, and 10. If we run sum is character, we're basically asking, is anything in this list a character or whatever, a character vector? Yes, letters is a character vector, therefore we get true. Whereas if we run every here rather than sum, we're going to get false because this isn't a character vector and that is not a character vector. And similarly, if we run is vector for every element, we get true because this is a vector of numeric values, this is a vector of letters, and lists are vectors. Does that make sense?
Yep.
Oh, lots of new functions I didn't know about.
Yeah, there's quite a lot. I think quite niche. So the next set is basically detect and detect index. So this finds the first element in the list or vector that you're iterating through where the predicate is true. So here, basically, if you do detect dot greater than 5, you're saying what's the first value in this list, in this vector, sorry, where the value is greater than 5. So, well, right off the bat, the first one is greater than 5. And if you want to know the index of the value rather than the value itself, then you use detect underscore index. head and tail while do the similar thing, but they give you all the values up to or from a certain predicate. So all the elements in this list, in this vector basically, go through this vector and check my predicate, i.e. is this value greater than 5? And give me everything that says yes until you reach a point where it doesn't apply. So is 10 greater than 5? Yes. Okay, keep it. Is 6 greater than 5? Yes. Is 1 greater than 5? No. Then I'm going to take all these values and stop considering after I've encountered a case which isn't true. And if you do tail, then you go the other way. So 7 is greater than 5, 9 is greater than 5, 8 is greater than 5, 5 isn't, so we're interested in these values. And the final sort of set of helpful functions are reduce and accumulate. So these are functions that you use if you want to go from a list or a vector into a single value. So reduce basically applies the function that you are interested in to basically pairs of values in your vector until you've run out of values. So, and I think I sort of shared this sort of cheat sheet, which I think demonstrates it in a really easy to understand way. Let me quickly get that. So basically, we're looking at reduce here. So we have our function and we have our list or a vector. So what this does is it takes the function and it applies it to the first 2 elements of the list, and then you get a result. So now you have basically the result of A and B, C and D. Then you apply the function to the new first 2 elements, right? So you take A and B, find the result, then you apply the function with that result and C. Now you get a new function, and you apply that with D, etc., until you've basically reduced your list into a single value. So you take these 2, and then result of that with the next, result of this with the next. So imagine if you're doing sum of basically reducing this list using sum as your function, you take A plus B, then you find a value, I don't know, 3. Now you take 3 plus C, and you find a value, let's say 5, and then you take 5 plus D, and you get your final result.
Yeah, so Havva, what is the use case for these reviews, please?
Good question. I don't know. I guess like whenever, yeah, I don't really know.
Okay.
I've not really used it that much myself.
Maybe in some kind of mathematical or statistical concept, they may need to do this kind of summations, you know what I mean?
Yeah. And a similar function to reduce is accumulate. So instead of basically caring about just the final value here, accumulate keeps the result of each step. So the first step is A and B, so you keep that result. Then the next step is the result of A and B and C, and then you keep that result. So sort of familiar accumulate function is the cumulative sum. So cases where you basically just keep adding values. So this is how you could do that sort of from scratch yourself. So you could do accumulate, and then .x would be the list that you want to get the cumulative sum of, and .f would be sum, the function sum. And again, you can imagine instead of a cumulative sum, maybe you have a more complicated value that you're calculating, or maybe you're taking certain conditions into account. You can sort of implement it yourself like this, rather than writing a for loop, iterating through everything.
So basically, and this is something I tried out one time. So what we've been looking at are doing whatever we want with the column or a list. For example, finding the type or the class of the column. But now we've reduced and accumulate. That means you could actually manipulate the elements of a given column. For example, if you want to calculate the return of a given column between two at every point, for example. Yeah. I'm thinking you could actually use the accumulate function to do that.
Yeah, I think, I don't know, like I find one use case of this like cumulative sum or cumulative product or whatever, a quite sort of easily relatable thing. But reduce is sometimes harder to imagine. But I mean, yeah, you know, if we search for use case for reduce function, there will be lots of examples.
Yeah, I can't relate to reduce, definitely.
Yeah, because I mean, I can imagine like if the function itself that you're applying is a very expensive function, as in like computationally intensive function.
Yeah.
And let's say you want to stop as soon as you read some sort of error, then this could be a way of using that. I don't know if that's necessarily a good use case for using it, but like if you have a break clause in there for a certain sort of error handling, then you don't have to run this computationally expensive function for everything. You stop when you reach an error. But yeah, there are probably, yeah, better use cases. But I've not really looked too much into it.
Yeah, but I mean, if you think about it, you can use reduce the same way as you are using accumulate. Just the difference is that with accumulate, you want to store every possible intermediate value.
Yeah. Exactly. I mean, accumulate is basically, sorry, reduce is basically you run accumulate, but you only take the final value.
Yeah.
It's exactly the same thing. And I think that's it really. Yeah, I've not had time to do the final set of exercises. Discuss them or do them together if you want. If you had any like problems, we could discuss them.
No, I'm happy with this for now.
Yeah, I think that's also, that's all I got.
Correct. Right, thank you.
No worries.
Yeah, thank you.